Here we are. We are working on benchmark 2 for 8th grade material. And what we'll see and notice that as we move through these benchmarks, we will repeat certain information. So we will be doing problems that deal with chapters 1, 2, and 3 from benchmark 1, and now we'll add 4 and 5. And so a lot of this in the beginning will feel like we've done it before in benchmark 1, which is nice because we want that type of review. And then on the latter pages, we will start doing things that is not familiar. So first thing, we have variables on both. We have multiple variables, multiple constants. So we're always going to combine like terms when they're on the same side of the equal sign. So we have 1/9 x minus 5/9 x, which is 4/9 x plus 16 equals -8. Now we've consolidated our variables. Let's move our constants over. We have 4/9 x equals -24. And now when we have a fraction, we are not going to divide by 4/9. We're going to multiply by the reciprocal, 9/4. And we're not going to multiply 9 times 24. We're going to cross cancel. We're going to reduce this fraction because it's a whole lot easier to multiply 6 times 9 or -6 times 9 to get -54 over 1 or -54. That's the most efficient way to do that. You wouldn't want to multiply by 24 by 9 and then divide by 4. That's too big a numbers. Here we have some simplification. We can't get into these variables because we have parentheses and Chewbacca. So we're going to distribute. We'll distribute this -5 times each of these terms in here, and we'll take the -2 times each of the terms inside here. -5 times 8 is -40. -5 times -0.5. First of all, I know it's going to be positive, and I know that it's going to be 2.5x. All right, I know that 5 times 5 is 25, and then I have one decimal place. -2 times 3 is -6. -2 times -0.4x is going to give me a positive, a negative times a positive. 2 times 4 is 8, and then I have one decimal place. All right, and now we have variables on both sides, constants on both sides. I'm going to move this variable to the other side by subtracting 0.8. That's -40. That's plus 17, 1.7x. We take the 1, borrow, and that equals -6. Now we're going to move our constants over. We have 1.7x equals 34. We'll divide it by 1.7, divide by 1.7, x equals, and we have 34 over, well, that's the same thing. We can move that decimal point over one place, and if we do it, that's going to move it over. So you get 340 over 17. And 17 goes into 34 2 times, so that's 20. So the answer to number 2 is going to be 20. Knowing my times tables, and it's not that I know what 17, the multiples of 17 are. I just know that 17 doubled is 34. So just knowing doubling is really important also of any number. So there are certain things that I have an advantage over because of the amount of time I've spent with numbers. And then there's just a lot of logic that we can utilize. How many solutions does the equation 1/4 times the quantity 20 minus 12x equals 5 minus 3x have? So remember, our choices are 1, infinitely many, or no solutions. And we're going to distribute this. So that's 1/4 times 20, which is 5. 1/4 times -12x is -3x equals 5 minus 3x. We'll move our variables, and we notice that when we move our variables cancel. And when they cancel and make a true statement, we are going to have infinitely many solutions. That means every number that you plug in will be a solution to this problem. Other ones will say identity. Other ones will say all real numbers, but they want to know how many solutions. And so the answer to how many solutions, there are an infinite many solutions. Number 4, the vertices of a triangle have the points A, -1, -1, B, 4, 1, 1, 2, 3, 4, 1, and C, 2, -2, 1, 2. And so there is our object, there is our triangle. It says vertices of a triangle, so that's why I knew it was a triangle. Okay, now we're going to translate that triangle 3 units up. Nope, 3 units to the left and 1 unit up. So I'm going to go to the left 3, 1, 2, 3, and up 1. And that is going to give me my A prime. 1, 2, 3, up 1. Oh, I don't like when they do that. That's not fun. So C prime is actually on A. And 1, 2, 3, up 1 is going to be B prime. And if we connect those, we have a similar object. And it wants to know what are the coordinates. So A prime, it's going to be 1, 2, 3, 4. So -4, 0. B prime is going to be 1, 2. And C prime is going to be -1, -1. All right. And remember, we can do this. This is advanced, but this is important, and I'm pretty sure they teach you this, is the transformation. So for every x point, we're going to go -3, and every y coordinate, we're going to go +1. So if we take our original A value, which was -1, -1, and we put it into this template, -1 minus 3, -1 plus 1, we would get -4, 0. And that would be our A prime. So it worked. I'm just showing you. And that's something that you should be aware of. It's good. It's another way of utilizing a transformation or a translation. Number 5, the vertices of a triangle. A is -4, -3, 1, 2, 3, 4, 1, 2, 3. That would be point A. 4, -1, 1, 2, 3, 4, -1. That's B. And C is -1, -4. 1, 1, 2, 3, 4. So that's C. Let's attach them. Okay. And now let's look and see, what are we doing? We're going to reflect the triangle over the x-axis. This is our x-axis, and that's it. So we're going to reflect it. So the distance away from the x-axis, 1, 2, 3, 1, 2, 3, will be my A prime. And C is 1, 2, 3, 4. 1, 2, 3, 4 would be my C prime. And B is going to be right here. That's B prime. Let's connect those dots, and we should have a figure that is identical. It's just reflected over the x-axis. And what are those points? Let's talk about what those coordinates are. Well, A prime is going to be -4, 3. B prime is going to be 4, 1, and C prime is going to be -1, 4. So some of you already see the similarities between the original point and the reflected point when we talk about the x-axis. So that notation will look like this. So we see that our x value stays the same, and we just need the opposite of the y. If we're going to reflect it, we want the opposite of y. So my a coordinate was -4, -3, and if we plug that in, that's -4. It's the opposite of -3, which becomes -4, 3 for my a prime, which is correct. And you can do that to all the points. The vertices of a triangle are A are 2, 2. This is A. B is 2, 4. And that's B. That's way too close. And 4, 2. 4. 1, 2, 3, 4, 2. Oh, that A is in the wrong. That's not B prime, sorry. So a couple things. I want that A on the other side. Let's put the B on the other side too. So B is over here. A is over here. Let's connect them. All right, rotate the triangle 180 degrees around the origin. So since it doesn't say counterclockwise, we're going to go clockwise. It would be in the same location either way when it's 180, but clockwise and counterclockwise is important. So if I rotate it around 180 degrees, I get A prime is going to be there. And if I do B, that's going to be right here, and C is going to be here. That's B prime. This is C prime. That's an ugly B. Okay, so there it would be rotated. If we took this and went to the origin and then out, it should get 180 degrees, which it does in this case. So we want each of those points to be 180 degree rotation. And what are the coordinates of the image? Well, the coordinates of the image, A prime is going to be -2, -2. B prime is going to be -2, -4. And C prime is going to be -4, -2. So when we rotate it 180 degrees, that translation looks like this: opposite of x, opposite of y. That's easy. So when we plug in the point A, which is 2, 2, and plug that in, opposite of 2, opposite of 2, that should be my A prime, and it is A prime. Good. Number 7. Number 7 wants to know triangle MNP is the image of triangle JKL after a reflection on the y-axis. JKL is scalene. Question A, is the measure of angle K equal to the measure of angle N? So we actually don't need to see this on a diagram. We could absolutely reflect it and look, but this is more based upon the understanding of is an image of something, and we have triangle JKL and similar triangles and what their properties are. So M corresponds with J, N corresponds with K, P corresponds with L, MN corresponds with JK, NP, KL, PM, LJ. All those have similar, they are congruent. So the question for A is measure K equal to the measure of N? So yes, they correspond. Yes, because they're corresponding angles. I don't know if we have a new one for B. No, let's go to B here. And then question B says, is the length side of JK equal to the length side of NP? No. JK is congruent to MN. So JK, MN, NP is KL. So that's a big no. Okay? So very important to understand those corresponding parts, corresponding sides, angles. Line S and line N are parallel. Both lines are rotated 90 degrees counterclockwise. about the origin. Are the images of the lines parallel? Yes, and we showed this. You could draw a line. Let's take 2 points and draw a line from it. And if we, are they going to be, yeah. If we rotate it, didn't attach, 90 degrees, 90 degrees, and we can move that point. That point was over here. And then we can take another line. Well, let's do this over again. Sorry. I'm trying to get them to be the same line. So let's do this. Let's do one red. Let's do this point here to this point. And let's do this point. Let's make them parallel. This point all the way to this point. Those are 2 parallel lines. Hopefully I can separate each one. If we rotate it 90 degrees, and we take this and rotate it 90 degrees, we notice that they are still parallel. So that's a great visual of how that works and why. Okay, and then we could apply those templates or the translation part of rotating it 90 degrees and still see that those values, and we could take the slope and we'd find out that the slopes are the same. When lines have similar slopes, they are parallel. You translate a line 9 units up. Is the image of the line still aligned? So we can take a line and we can move it up 9 spots, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it is still a line. So yes, it's still a line and it's parallel. That's not a question, but that's a good one. The vertices of a triangle, -2, 3. -2, 3 is A. B is -1, -1, -1. That's B. And C is 0, -1. Okay, C. And let's connect them. Now let's see what we're going to do with that triangle. Dilate the triangle using a scale factor of 2. So scale factor of 2 is meaning we're going to make it 2 times bigger. So each point, A, -2, 3, is going to get 2x, 2y. So A prime is going to be -4, 6. So let's draw that one. -4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So this is A prime is -4, 6. Let's do B. B is -1, -1, and we're going to apply that 2x, 2y. So B prime is going to be -2, -2. -2, right where B is. Get out the way, B. We'll put B up here. And my new 1, 2, 1, 2, this is going to be B prime. And C was 0, -1. C prime is going to be 0, -2. Let's do that. So 0, -2. So that is C prime. And if we connect the dots, we get an object that is 2 times bigger. It's dilated 2 times. Scale factor of 2. Cool. I like scale factors. Scale factors can be fun. They can also be really hard and not fun. All right, describe the sequence of rigid motions between the triangles. I'm thinking that if you take, let's do this. We haven't done this before. Let's change the color for a second. Let's make it dotted. If I take this and go to the center and go like this to the center, can I see how much I rotated it? Yeah, that doesn't really look like an angle that I want to rotate. If I mount to the center, sometimes we don't. What if I did, what would that be? That one would be that would be 90 degrees. And if I take, let's do another color. Let's take this one. Let's go to here. Wow. Stop. Why aren't you drawing a line? Sorry. I must have clicked out. So if I go to the center and I go, oh, I didn't want that. I didn't want that. I want that red. Sorry. I wanted that red. That's 90 degrees, would end up there. And then if I wanted that point, 90 degrees, one, and notice it's 2 units, and then one would be here, right? I mean, let's do this, blue. So if I rotated it 90 degrees, it would be here. And then let's take another line, and let's take this, which is, let's change that color. Let's make that green. Green. Okay, so, and if we did that 90, what's that? That is 4, 3. So where's that going to go off to? 4, 3. 4, 3 is going to be there, right? Yeah, that's good. I want that green though. Green. And then if I take those dots and connect them, let's connect those dots. That goes here to here to here. Okay, that's my, oh. Yeah, see, that's not enough. Yeah, I would have to rotate even more. So that was 90 degrees. If we rotated that another 90 degrees, or if we rotated it, maybe that's what it was. And look, here's a great example of not doing it correctly the first time. I had a guess. I tried it, and it didn't come out correct. So I rotated that 90 degrees. Remember, what rotation of 180 would be is just the opposite. So you're just putting it down underneath. So maybe let's try that. Let's take this. Let's do this. Let's take this point. So if I opposite should be here. So is that the point? Yeah. And then opposite would be here. That would be rotating it. And then opposite would be for -3. And now we have my new object. Okay, that's rotated 180 degrees, which is a whole lot better looking. And then, remember, it's just -x, -y was the 180. And now I'm going to move this point 1, 2, 3, 4. So that actually maps better. So I would rotate, and that was 180 degrees. Clockwise, counterclockwise still gets us there. And then we would translate up 4. There we go. All right, took me 2 swings at it, but that's okay. Number 12, describe the similarity transformation between the triangles. All right, so let's take the small one and, well, if we rotate that, no. Oh, over the y-axis. I like that. Let's reflect it over the y-axis. If I reflect it over the y-axis, I get this, right? I think that looks pretty good. If I reflect it over the y-axis, that's just changing the x value. And then, let's see, that is, this is 2, so that's, so that, let's take this point. Let's take that little point here. We'll call that, we'll call that A. We'll call this point A, and A, that's kind of like A prime, actually. We'll call it A prime. A prime is 1, 1. And now this would be A double prime, and that looks like 6. Ooh. That looks like -6. And so is that not... that looks like 1, 1. Oh, no, sorry. It's -2. Hello, A prime is -2. Duh. -2, -1. I'm not even thinking. -2, -1. Right? -2, -1 is my A prime. So my A double prime looks like that is -6, -3. Okay, so what type of dilation would be that? That would be a dilate 3, right? We would dilate it 3, scale factor. I think we call it scale factor. That would be the second step, step 2. And step 1, if you remember, was reflect it over the y-axis. Reflect over y-axis. Because we reflected it to get A prime, and then we dilated it to a scale factor of 3 to get A double prime. All right, cool. And that's it. Okay, so again, the more we practice this, the better we become with some of these terms, some of these techniques. Keep at it. It's very important. You will definitely see these things on HSBT, on STAR testing, on your SAT. So